Hello, everybody.
Hello.
Hello. How's everybody
Hi.
enjoying our nice, cool fall, crisp weather?
Yeah, it's going good.
Still got some folks joining in here. Okay, well, let's get started. We're gonna talk tonight about a whole brand new subject. Tonight, we're going to get into torsion design. So before we dive both feet into the pool first, does anybody have any questions they would like to ask me about homeworks or any other subjects before we get started?
On the homework, the problems, there's like one that says like RP. Is that the review problem or something?
Yes, it is. Uh-huh.
Okay, thank you. I just wanted to make sure.
Yeah, yeah. In fact, what was the number of it? Do you remember?
I do not. I can check though.
There's actually a couple of them. I think one of them was R31.
R31? Okay. Let me find R31. That's a good one. Okay, so yes, and when it says R3-1, that is the first problem of the review problems on page 120 of your text. So yeah, there's a number of those in this assignment. So yeah, make sure you do R31 and not just 3-1. Okay, any other questions before we dive in? Okie dokie. So like I said, we're going to start a whole new section. I believe this is chapter 5. So you should be up and reading into chapter 5. And give you a little more specifics here. Chapter 5.1, 5.2. I'm going to talk about 5.3, but I'm going to talk about that next Tuesday. So you can kind of skip over 5.3 for now. And then we're going to get to chapter 5.4. So tonight we're going to be covering 5.1, 5.2, and 5.4. And then we'll finish up on Tuesday with the remaining topics in torsion. Okay, so what is torsion? Torsion is a bending moment, but is orientated along the longitudinal axis of a member as to cause the member to twist. So here's a axially or a long, slender member. This dumbbell looking shape here is really kind of the best I could do to represent where it is fixed to the wall or fixed to some kind of a support. So anytime you see this little flanged dumbbell looking thing, that's my representation that this is fixed to a support at that point. If it doesn't have the dumbbell like here, then it's free to deflect or twist or do whatever. Okay, so if we imagine a rod before the application of torque, then we're going to put this little grid system on here so you can kind of see what's going on. So the same, only we're going to line it up with some grids on here. And then applying the torque, we can see that the rod is going to twist. Okay, so it twisted. You see that these lines now have an angle to them. They're not perfectly straight anymore. If I go back, that's undeformed and deformed. So at the fixed here, clearly all the lines are exactly where they were. It doesn't move at all where it's fixed. It moves or twists the very most right out here at the very free end of it. And all of these longitudinal lines then basically take on a straight line, but they warp from zero deformation or zero twist to maximum twist at the end of the rod. As the rod twists, notice the radial lines at the end of the rod remain straight. So these lines here don't warp, they stay straight. As we do one more twist there. So now we got more twist on it. You can really see these lines are twisting, but the radial line, that whole circle at the end turns, but everything remains plain and straight. The longitudinal lines along the length of the rod warp as the rod twists. Okay, any questions on this? Okay. So here's our undeformed shape, and here's a deformed shape with a twist to it. And if I was to look at like just one little slice here, kind of looks like a banana, huh? That you would slice up into slices. If I look at just one little slice of the banana, what this is showing is that this inside disc has turned more than the outside disc. And so you get this warpage on here. And I found some other illustrations that kind of demonstrate this. So before the twist, this panel right here is square. But after the twist, this panel has warped. So it's not square anymore. And it's this warping that looks a lot like our shear strains, right? Remember all the stuff we did on something that started off as square and then it underwent some shear strain and now it's more like a parallelogram. That's the shape that this takes. So we're kind of looking at the skin on the surface of the rod, and as it twists, the skin is going to warp. And the main point of that is that the warpage causes shear stress. It causes a shear strain and it causes shear stress. Okay, so from this illustration, you can see that the maximum warp is at the furthest distance from the center of the rod. So here's the center of the rod. Rho here represents a radius distance. C represents a radial distance as well. And what this is kind of showing here is that as this inside circle turns more than the outside circle, you get this gamma max. And the gamma max is this angle that is turned from the inside to the outside circle. That is a shear strain. And gamma max is maximum at the surface of the rod, and it is less and less as you get towards the center of the rod. At the very center of the rod itself, there is no differential rotation, there is no shear strain, there is no shear stress at the center of the rod, and it progresses outward in a linear fashion. This is what this is illustrating. So therefore, the shear stress induced by the twisting warp is proportional to the distance from the center of the rod. As illustrated, the shear stress increases linearly from the center of the rod, and that's this illustration here. So at the center of the rod, there is no shear stress induced. At the perimeter of the rod or the surface of the rod, you have your maximum shearing stress. And that shear stress is both in the perpendicular direction, but it's also in the like in and out of the page longitudinal direction. Because, let me go back here a little bit. This is the element on the skin. This shearing stress would be the one represented by in and out of the page, or I'm sorry, the one that's in the plane of the page, this shearing stress would be in and out of the page. Anytime that you have shearing stresses, they all have to equalize each other. So it causes shear stress this direction, and it causes shear stress in the radial direction. This is representing the shear stress in the radial direction, but looking from the section of the rod. And the main point here is that the increase in stress is proportional to the distance from the center of the rod. So far, so good? Everybody all right?
Can you repeat that last part just one more time?
The magnitude of the shear stress that is induced by torsion is proportional to the distance from the center of the rod to the extreme perimeter of the rod. So the shear stress is maximum at the surface, and it is equal to 0 at the center of the rod. Anywhere in between the two, it's a linear proportion. Okay, which I'll show here. So if we define C to be equal to an arbitrary distance from the center of the rod to a point, any point along here, then the shearing stress tau, remember tau represents a shear stress, at that location is equal to, tau is equal to the applied torque times C. C is the distance from the center to the point of concern, divided by this J. And this is known as the torsional equation. And so you can see that the shear stress is directly proportional to C. C is the distance from the center to the end. If C is equal to 0, there is no shear stress.
What
So-
is J? Excuse me.
Yes. What is J? Coming right up. First, T. T is your applied torque, and torque is a moment. It's just applied in the longitudinal twisting direction. So the units are kip inch or pound inch or Newton meter or kilonewton meter. Little c is the distance to the point of interest from the center of the rod, measured in inches or millimeters. And J, to your question, J is the polar moment of inertia. So like moments of inertia, it is inches to the fourth or typically millimeters to the fourth. Again, tau is maximum at the outside surface of the rod.
Excuse me, Professor.
Yes,
So moment of inertia of what?
it's called the polar moment of inertia. And it's going to be the moment of inertia of this round section,
Okay, got it. Thank you.
because it is the size and the section properties of the circle that will be resisting a twist. So actually, before I hit you with exactly what that equals, let me show you this. Clearly, if I put a known torque on the end of this rod, if this rod is a 1/2 inch diameter, it's going to twist a lot more than if it's like a 5-inch diameter. So the polar moment of inertia is basically the resistance due to the section size of a rod to resist twisting. And for a solid round bar, polar moment of inertia is equal to pi over 2, and C is the radius of the bar, C to the 4th. So
And
again,
this equation, it works no matter what material we use?
yes, it does, because it's a property of the section, not a property of the material. That's a great question. Yeah. If you had a 1-inch diameter bar of balsa wood, and you had a 1-inch diameter bar of, I don't know, titanium, it would have the same polar moment of inertia. Okay, and then I was going to say is that C again is measured in inches or millimeters. So when you do C to the fourth, you're going to get a polar moment of inertia with units of inch to the fourth or meters to the fourth or something like that. If you have a hollow bar, otherwise known as a pipe, that has an outside radius and an inside radius, then the polar moment of inertia for a hollow pipe is pi over 2, outside radius to the fourth minus the inside radius to the fourth. Okay, any questions on polar moment of inertia? Okay. So let's do an example. For a solid round bar, like so. So again, this is the free end, this is the fixed end, this is a solid bar, and it's 18 inches long with a 50 kip inch applied moment. If I call the bar diameter, and we use phi here, this is kind of typical in the industry, we use phi to represent diameter. So this means the diameter of 2 inches. So what's required is, what is the maximum shear stress in this bar due to this applied torque? Wow. You ever get a phone call that says potential spam? That's pretty nice. That way you don't have to worry about it. Okay, so solution. The maximum shear stress will occur at a maximum distance from the center of the rod or at the radius distance. So we're going to make C equal to 1 inch. Clearly, if the diameter is 2 inch, the radius is 1 inch. The polar moment of inertia for a solid bar is J is equal to pi over 2 C to the fourth. So I have pi over 2, 1 inch radius to the fourth is 1.571 inches to the fourth. The applied torque is given as 50 kip inch. Therefore, the shear stress is tau is equal to TC over J. So 50 kip inch times 1 inch over 1.571 inches to the fourth. Notice that I've got kip inch squared over inch to the fourth. So my answer is going to be kips per square inch, right? It's going to be KSI. That's good because I'm looking for a stress. You can always use your units to make sure you're on the right track. So 50 times 1 over 1.571 is 31.83 KSI. So that is the shear stress. That shear stress is going to occur right on the surface of the material due to this applied torque. Now let's say, oh, I'm sorry, go ahead.
So we're gonna get same shear stress at any any distance in the in this 18 inches, right?
Yes, you
like
are.
Any same.
Yes. Yes.
Okay.
Good question. Because this is applied at the end here, and I'm fixed at the other end here, what we're going to find is that the torque is constant along the entire length of this 18 inches. It has to be because there's no other torques applied or anything to diminish that torque. So this is going to be a constant torque of 50 kip inch. So that means that any section along here, I could cut here, I could cut here, anywhere that I cut, the internal torque is 50 kip inch. So this 50 kip inch applies anywhere along the length of this rod. And at any place along the skin or the perimeter of the rod, the radius is still 1 inch. Anywhere. I could look at it here, I could look at it over here. Anywhere that I look at the surface of this rod, the radius is 1 inch and the internal torque is 50 kip inch. So this stress is going to be constant from the support to the free end all the way around this thing is going to be in a constant 31.83 KSI of stress. Okay, but what if I want to find a shear stress at a distance of a 1/2 inch from the center of the rod? So not at the skin, but halfway. What is my stress halfway? Since J is a function of the rod and the torque is given, of this equation here, the only thing that would change is little c, the radius. So here's a cross section. Really, anywhere along this rod, this is a cross section that looks like this. We just found that this stress is 31.83. What is this stress right here at a 1/2 inch? So I go back to my torsional equation. Tau is equal to Tc over J, which is 50 kip inch times a 1/2 inch radius over my polar moment of inertia, 1.571. The polar moment of inertia does not change. That's a function of the whole section. The torque doesn't change because it's constant. The only thing that would change is the radial distance. And the answer is 15.91 KSI. So if I'm halfway to the surface, I have half the stress. And of course, box your answers. Any questions on that example?
Can you go back to the slide? Thank you.
Okay, let me know when you're ready.
Yeah, that's it. Thank you.
Okay. All right, so the next big topic for tonight is angle of twist. So if I have a bar fixed at one end, apply a torque to it, as we already said, the end of this bar is going to twist. Well, how much is it going to twist? So I'm going through this again. You can see that if I grid it out and then apply a torque, you can see that it rotates and rotates. So if we section the rod into differential discs of thickness dx, here's this illustration again. So the thickness of this little slice is dx. Then we see that under a torque of T sub x, some arbitrary torque at some arbitrary location, the near plane rotates relative to the outside plane. The difference is labeled as d theta. Okay, so here's d theta right there. And d theta is a measure of how much the inner circle has moved relative to the outside circle. This d theta, or d phi, I guess that's d phi. This d phi deformation causes a shear strain, gamma, that is proportional to the radial distance, rho. Okay, so again, here is gamma right there. It's this triangle. So if you can see where I'm pointing to, you can see this triangle. Well, the angle of that triangle is gamma. And gamma is something down here, but gamma max is at the surface here, like we just said. So, but for every shear stress, there's a shear strain. Gamma is the shear strain due to the torsion. Okay, so from the illustration and using sine of small angles that we talked about earlier, we can relate that rho d theta, okay, so here's rho at some arbitrary distance, times d theta, which is this angle here on the face of the disk. So rho d theta, and where did I put that? Oops. There it is. Okay, so rho d theta, here's d theta, that triangle, and here's rho. So small angle tells us that the red line that I drew in there is that length, rho d theta. So it would actually be like rho times sine d theta, but the sine of a small angle is equal to the angle. So rho d theta is equal to dx gamma. And so here's dx is the thickness of this little slice, and gamma is this angle here. So we're kind of coming at it from two different directions. We have a triangle on the face of the disk, and we have a triangle in the thickness of the disk. And the red line is the result of both of those, and they are equal to each other. Okay, everybody see that? Anybody not see that? Okay, anybody see that or anybody not see that? Should include pretty much everybody. Is there anybody out there?
So
Yeah,
the
that makes sense.
so the gamma is the thickness of what you cut.
dx is the thickness.
Oh, dx is the thickness. and-
Yeah, yeah. So dx is this line right there.
Okay.
And then, you know what? I wonder if, let's see if this would help. Okay, let's see if this helps. So from here to here is dx. That's the thickness of the slice. And this angle between these two surfaces right there, that angle is gamma.
Oh, okay.
Okay. And then I can't, oh, that's on the, okay, I can't get rid of that one. Okay, but now from the other direction, if I take rho all the way to the surface like this, and then I create this angle here, this angle is d theta, or d phi, I'm sorry, d phi, and d phi times rho, which would be the distance to the surface, is equal to this length right there.
Mm-hmm.
Okay.
Okay. Yeah, that makes sense.
Okay, good. So let me get rid of this and this. So basically what really all we've done so far is just say that this distance times d phi is equal to this distance times gamma. Gamma is an angle, d phi is an angle, and so we're just basically saying that this times that angle is equal to this times that angle, because that red line is the same red line from either direction. Does that make sense?
Yes. And it's just phi times d theta because it's just the small sign.
Right.
Okay.
Yes. Yeah, exactly.
Thank you.
Okay. All right. So let's get back to slideshow, current slide. There we are. Okay, now we're back. Okay, so that's why this is equal to this. And we're going to use this to kind of build our theory. Okay, so here, all I've done is just rearranged my variables. And I solved for d phi. D phi is equal to gamma times dx over rho. And then from Hooke's law, I can add this material. Gamma is equal to tau over g. This is exactly the same expression of Hooke's law as epsilon, the average normal strain, is equal to sigma stress over Young's modulus E. This is the exact same thing, only this is in shear. So shear stress and shear strain. So the shear strain gamma is equal to shear stress tau over G, which is the modulus of rigidity. Okay, so this relates gamma to tau and G. From the torsion equation, we have tau is equal to, in general, a torque as a function of x times rho over the polar moment of inertia as a function of x. So we can substitute, and I put this into here, and I get that gamma is equal to tau, or excuse me, torque times rho over jg. And it looks a little more complicated because everything's a function of x, but we're keeping it general. Okay, so gamma, if I plug this gamma up into here, you see that the rho and the rhos cancel each other. And so d phi is equal to gamma dx, or torque over jg dx. So this is my generalized form. And also remember that dx is in the direction of the longitudinal axis, and phi is a rotation, a twist. Okay, so I just reproduce the same. D phi is torque over jg dx. And this is an illustration of what we're doing. The torque is an arbitrary torque at an arbitrary location x, and L is the overall length of the member. So now what do we do when we have a d phi and a dx? We have to integrate. So when we integrate, we get phi. Phi is an actual twist. It's a measurable rotation. And phi is equal to the integral from 0 to L, so from 0 to L, of the torque over the polar moment of inertia and the modulus of rigidity dx, where phi is the angle of twist from one end relative to the other over the length L, and we measure that in radians. T sub x is the internal torque as a function of x. I underlined that because that becomes a source of confusion. This is not the applied torque necessarily, it is the internal torque. And I'm going to get back to that a little bit later. We're going to talk about internal torque. But this is an internal force in the member due to external forces.
Excuse me, Professor.
Yeah.
So why you integrate? Like, do you have like different diameter?
You may, you could. So if you had a,
Because if everything like it's constant.
well, but what if it isn't? What if it isn't constant? What if this is a 2-inch diameter rod that skinnies down to a 1/2-inch diameter rod?
And this way we have to integrate.
Yeah.
Yeah, but in the image, like I see everything like it's constant. So
In the
that's
image,
why
absolutely, yes. But this is the general form, because you may get a situation where any one of these three are not constant. J of x is the polar moment of inertia as a function of x. Again, you could have a conical shaped, or you could have different shapes at different locations. I only showed one. And the modulus of rigidity as a function of x would not be very common that this changes as you go down the length of the same material, but you could have segments welded, bolted, fused together in some way of different materials. So it wouldn't be constant through the whole length. And L is the length of the rod in question. Okay, so as we were saying, this is the general solution. Any of the three variables that may be constant along the length L come out in front of the integrand. So if all three of them are constant, right, then this reduces to something pretty simple. If all three variables are constant, at least for segments, then the angle of twist equation reduces to phi is equal to TL over JG. That's the simplified form from the generalized form, right? And that's what you were just asking about?
Yes, thank you.
Okay. So notice the similarity to the axially loaded member. when we had axially loaded members, we did through the same thing. We had a general form, and then we had a simple form if everything's constant. And the simple form was delta is equal to PL over AE. Here, V, the radiant twist, is TL over JG. So everything is analogous. Just instead of area, you have a polar moment of inertia. Instead of Young's modulus, you have the modulus of rigidity, L and L, and axial load versus a torque. So like the axially loaded member consisting of segments, so if you had several different segments of constant load in section of each segment, then like the axially loaded member, we can do the sum of, and we can do the sum of individual segments from I equals 1 to n number of segments. Again, very similar to delta is equal to the PL over AE summation of segments. Okay, any questions? Ready for example? Okay. For a solid round bar, okay, this is the same sample that we just did a little while ago. So, but I'm going to change the bar diameter to 3 inches, 50 kip inch over an 18-inch length. The bar is A36 steel. And what is required is tell me the twist at the end of this bar due to this loading. Solution. Okay, if the bar is a 3-inch diameter, then the radius is 1.5 inch. So the polar moment of inertia for a solid bar, J is pi over 2 c to the 4th, which is pi over 2, 1.5 to the 4th, which is 5.063 inches to the 4th. Because of this to the 4th, these get really big or really small really quick. It's amazing how much larger a 1.5 inch radius is from a 1/2 inch radius. It's really crazy. From the back cover of the text, you will find the tables. I'm sure everybody's familiar with these tables by now. You find G, the modulus of rigidity for A36 material. And you'll see that it's 11,000 KSI is that value. So the applied torque is given as 50 kip inch. The torque is constant along the length because it is applied here and we're fixed here. Nothing else is happening. So this torque has to be constant along the whole length. So I can use my equation because the section is constant, the load is constant, and the rigidity of the material is constant. So all three are constant. I can use my equation, 50 kip inch times 18 inches long, 5.063 inches to the 4th, and 11,000 KSI, and I get 0.0162 radians. This thing's going to twist in the direction shown for this. That's an angle, really. So that's a measure of how much it is going to twist. And you box your answer. Any questions?
Is the twist always in radians?
Well, yes, it should be. But there really is no reason why you can't report it in degrees. An angle is an angle. Any angle could be measured in radians or degrees. It's just that typically speaking, the twist in some kind of real material, some structural element is not going to be very much. It better not, or you've grossly undersized it if it's very large. So generally speaking, degrees are kind of inadequate to describe the twist because degrees are too big. But radians are much, much smaller. But having said that, maybe it is more of just a preference because, like I said, any angle of rotation can be measured in either system. Phi is an angle, yes. Any other questions? Yeah, if you get, say like you had this rod, and that rod is 3-inch diameter, so that's like, I don't know, like this, like a softball bat, and it's only 18 inches long. If you got that thing to turn like 45, 50 degrees, pretty much it's got to be made out of some kind of foam or rubber. You're not going to get a structural material to do that. Okay, let's talk about sign convention. For the directionality of torques and twists, we will use the right-hand rule. So if I'm looking at a section like this, or this is my my rod that is in torsion, and this is a cut, so I'm looking at internal forces, then we use the right-hand rule. And the right-hand rule is basically that from the cut surface, you extend your thumb out in the opposite direction, away from the cut surface. And then you curl your fingers in using your right hand. So what's illustrated on the screen is a positive torque from this direction. If you take a bar from the other direction, then you extend your thumb out from the cut surface and you curl your fingers. So this would be a positive torque from something cut on this side. Okay, so does that read to everybody? Right, so to keep your signs correct, always use the right-hand rule. For both halves, the internal torque is shown as positive. So this is the same torque. It's just on, when you cut it on this side, it's twisting, what would that be, counterclockwise? And when you cut it on this side, it's twisting the other way. These are both positive torques. In each case, extend your thumb from the cut surface and curl your fingers for a positive torque. Okay. Next topic is torque diagrams. These can be extremely helpful for seeing the torque at any segment. Remember, we just talked about to find the twist of something made of segments, you have to add up what's happening in each segment and you add those together. So you need to know what the torque is in each segment, and a torque diagram is very helpful for discovering that. If our loading diagram looks like this, okay, so here's a bar of different size segments, and I have different loadings applied at various places. This segment is 15 inches, this segment is 9 inches, and just for the sake of clarity, I only put the applied torques at the terminals of these different segments for simplicity. But can you all look at this and tell me what is the internal torque in this member and what is the internal torque in this member? Is that something you can just look at and instantly know?
No.
I'm glad you said no, because if anybody had said yes, then I'd make it harder.
We need the diameter.
So I want to cover this carefully because I've had students that got confused about applied torque and internal torque, and they are very different, or they can be very different. Just because you see a 20 right here, that does not mean that the torque inside this member is 20. Just because you see 55 here does not necessarily mean that the torque inside this element is 55. You have to map out the whole thing before you decide what the internal torques are. And the first step to doing that is to create a torque diagram, is to find your end reaction. Don't even attempt to guess what these torques are internally until you get your end reaction. As so. Okay, so how do you get your end reaction? You need to sum your moments. External load is always the same, but internal load vary. Well, the external load is typically given. Somebody has to tell you what is being applied to the member. Or you can calculate that or figure out what's being applied. But once you know what the applied loads are, then we need to go through these steps to find the internal loads. Does that make sense? Okay, I won't forget you, Dima. Let me walk through these steps and then tell me if you're still not 100% convinced. So the first thing we're going to do is this is where the whole rod is fixed at this end here. So I'm going to assume a reaction. I don't have to guess it correctly. Just like when we did horizontal and vertical reactions, you don't have to guess them correctly. You just make a guess of which direction that reaction is, and then you sum your moments. So using the sign convention, like so, right? So if I stick my thumb out here, this is a positive 20. But if I stick my thumb out here, this is a negative 55. That's my sign convention. And if I stick my thumb out over here, as I've drawn it, this is a positive reaction at A. Okay, so using my sign convention, this is minus 55 plus 20 plus RA, and everything has to equal 0. Okay, before I go one step further, does everybody understand why this is negative, why this is positive, why this is positive? Okay, I got one yes. Anybody else? This is super critical that you are able to see why this is negative, why this is positive, why this is positive.
Yes, it makes sense.
So this is gonna be the moment at the axis, right?
Yes, it is. Yeah, it's a twisting moment.
Okay.
Yeah. So when I say sum the moments, it's really kind of saying the same thing as summing the torques.
Mhm.
Okay. So yes. All right. So if everybody is comfortable with why this is negative, why this is positive, why this is positive, then I will solve my equation. And I find that RA is a positive 35 kip inches. The positive on my reaction means that I guessed the direction correctly. So I put in that direction. I have to indicate on my answer the direction of my reaction. Remember, all reactions have to have a direction associated with that reaction. So this is my positive reaction. And that's what I just said. Okay. Now, to find the internal torque at each segment, we need to make a series of cuts and take a free body diagram of each piece. Okay, so I redrew my problem statement, but now I've got my 35 kip inches drawn in the positive sense. I have my positive 20 and my negative 55 here. Cut number 1 is going to be between A and B, like so. And cut number 2 is going to be between B and C, like so. These two cuts will allow me to solve for the internal torques between A and B and C. If by, just as an example, if the problem had another applied torque, say somewhere in here, then what would you have to do?
Take another cut.
Thank you, exactly right. You'd have to take another cut, one on the far side of that applied torque and one on the near side of that applied torque. Exactly. Okay, so let's work with cut number 1 first. And there it is. I cut through and I'm only looking at, and it doesn't really matter. You could look at the left-hand side or the right-hand side. I chose to look at the left-hand side. So I made my cut and I put in there a torque AB. Again, I don't know what the sign of this is yet. So I drew it and it's a positive torque. So a positive torque, again, stick your thumb out from the cut surface and curl your fingers, and that would give you that torque AB as drawn is positive, okay? So whenever you're making a cut and you don't know what the sign is yet, always draw it in the positive sense and then solve for it. So I've drawn A as it is, and I've drawn the torque internal unknown in the positive sense. Sum my moments. I have 35 kip inches plus TAB is equal to 0 because they're both going in the same direction. So TAB has to be minus 35 kip inches. Now, this is an internal force, so no direction arrows on internal forces. You just tell me, is it positive or negative? And this, it would be a negative torque.
Professor, quick question. So I know that torque is kips per unit length. So since it's per inch or times inches, we don't have to multiply the distance when we're taking the moment?
Okay, let me try to attack that question. First of all, please, please, please be clear that a torque is a moment. It's just a moment that is twisting on the longitudinal axis. So the units of a torque are always going to be a force times distance. They're not per any distance. They're a force times distance. So it's going to be kips times inch or newtons times meter, whatever, but it's always a force times distance. Okay, so that's the first part. The second part is that the torque is already a moment. If you had a force applied here, then a force would have a lever arm or a lever arm. And so to get a moment due to a force, you have to multiply the force times its effective arm. But a torque already has, it's already a moment. Does that make sense?
Yes, it does. Thank you.
Okay. Okay. So yeah, you don't multiply this times any length because it's already in the form of a torque. Okay. So I found that the internal torque at A to B is minus 35 kip inches. Now we move to cut number 2. And I make my cut. Again, it's arbitrary if you want to do the left or the right-hand side. But what is important is that you put everything on there consistently. So I have 35 kip inches positive. I have 20 kip inches positive. Again, I'm using the right-hand rule. And I draw my unknown internal torque TAC or BC, TBC in the positive sense. Okay. The internal torque between A and B does not go on this diagram. It's internal. We're only putting the externals. Sum the forces. I have 35 plus 20 plus TBC is all equal to 0. So TBC is equal to minus 55 kip inches. It too is going to be negative. You could get to the same answer by taking this cut 2 and only looking at this side, in which case you would see that this applied torque is a negative torque. So the internal torque would have to be negative. Okay, so now that I've solved for TAB and TBC, we can now construct our torque diagram. TAB is minus 35 as we found, TBC is minus 55 as we found. So now you draw this. So from A to B, this was 15 inches, and it's a constant minus 35 because there was no other torques in between there. There was no rigidity or fixture in between here, so the torque has to remain constant. Between B and C, likewise, it's a constant minus 55, so this is your torque diagram. With the torque diagram, we can now visually see the internal torque at each segment. I can look right at it and say, okay, from A to B is a constant minus 35. From B to C is a constant minus 55. Okay, any questions so far? And Dima, you had your question earlier. Did I hit that question, or are you still not convinced? Okay, great. Okay, so now I'm gonna do a final example that's going to illustrate, if I back up here a little bit, that's going to illustrate how to use the sum of the segments to find the total twist at the end of this rod. Okay, so if I define that segment AB is 2-inch diameter A36 steel, and segment BC is 1-inch diameter A36 steel, then can we find the radian twist at point C? And here's the problem. This is the original problem. So this is point C here. Can I find that radian twist at this point? So the radius of CAB is 1 inch. So the polar moment of inertia at A to B is pi over 2 C to the 4th, pi over 2 1 inch to the 4th, 1.571 inches to the 4th. For CBC, the radius is a 1/2 inch. So the polar moment of inertia is pi over 2 C to the 4th. Put the 1/2 inch in there, and look at this. You reduce the radius by half, and the polar moment of inertia is like 1/100th or 1,000th of what it was before. It's really amazing. So this little portion is going to be much more flexible than the rod of twice the diameter. For A36 steel, we already found the modulus of rigidity is 11,000 KSI. And so I use my sum of the segments. So phi, the twist, is minus 35 kip inch times 15 inches over my J of 1.571 inches to the 4th, and also over 11,000 KSI. This is I equal to 1. So this is my first segment. And oh, by the way, I forgot to say, I know I can use this equation because within each segment, J is the constant, G is constant, and we know now from our torque diagram that the torques are constant within each segment. So now my segment 2 is minus 55 kip inch times 9 inches over my pathetically small J of 0.098 inches to the 4th over 11,000 KSI. And my final answer is minus 0.4896 radians, which is actually something like 27 degrees. This thing really wants to turn when you put it on a 1-inch thick rod. Okay, any questions at all?
Is that fee for the whole thing or just like
Oh, that's a great question.
one part?
That is just for one part. That is only for the twist here at C. Remember, we started the presentation, I showed you the twisted rod with the longitudinal lines that are twisting. So the twist at A is absolutely 0. There's no twist at A because it's fixed. The twist at C is the maximum of minus 0.4896 radians. So let me ask you a question. I think, Nick, you're the one that asked this.
Yeah.
How would you find the twist at B right here? What is the twist at B equal to?
Is it the difference from A to B and B to C?
If I wanted the twist right here at B, then I would only use this part of the equation. The twist from, okay, so remember, phi is the difference in twist. So the difference from the fixed end to B is equal to the torque times the distance from A to B over JG. So the twist at B would just be this term right here. What if I asked you, what is the difference in twist from B to C? We know B is going to twist a little bit. C is going to twist a lot. What is the difference in twist from C to B?
Would that be the other half of that equation?
Yes, it would. It would just be this term would be the difference in the two. So this equation here is really the general equation to find the difference in twist between any 2 points. And the distance between those points is the L that you plug in here. So we could take it one step further. We could say, I want to know what the twist is right here in the middle between A and B. Can we do that? Sure, we can do that. From A to B, the torque is 35. If I want to know what the twist is halfway, I put 7.5 inches right here instead of 15. And from A to halfway, the J and the G's are constant. So all I would have to do is just use this term and put in 7.5 inches. And that would give me the twist right here. What if I want the twist halfway between B and C? Well, then I would have all of this term, but in this term, I would just put in 4.5 instead of 9, and that would give me the twist halfway. Is this making sense? Are you guys seeing this?
Yeah.
Yes.
Yeah.
Yeah.
Okay, great. Alrighty, any other questions on this torque? Or before I ask that, the plan is for, what is today, Thursday? The plan for next Tuesday is we're going to go through another series of problems that is an indeterminate structure. And so that's going to be very much like what we did with axially loaded members, but they're going to be torsionally loaded members. And we'll talk about how to solve those. And then we're going to touch on power equations just a little bit. And so next Tuesday, we'll wrap it up for us for all of chapter 5. So please pre-read chapter 5 when we go into our lecture on Tuesday. And then after that, we're going to get to some fun stuff with chapter 6 and bending. Okay, so that's the plan moving forward. Do I have any questions for tonight?
Yes, Professor. How many sections do we cover today?
5.1, 5.2, 5.4.
Thank you.
Any other questions?
So this might be looking ahead a little bit, but if we were to have a force that was acting, say, on the axis that the torque is, would it change the value of the torque, so to speak?
Okay, let me draw this, see if I understand you right. So if you had a force going this way,
Yes.
okay. No, it would not change this at all. But remember the principle of superposition? you can find all of your deformation and stresses due to the torques, and you can find all of your deformation and stresses due to the normal force, and they don't add to each other. One is a normal stress, the other one is a shearing stress.
So the torque like causes only the shear stress.
Torques cause only shearing stress. Yes. At least for the purposes of this class. When you get into more advanced topics, it does get a little more complicated, like reinforced concrete beams. When you apply a torsion to a reinforced concrete beam, the concrete tends to try to crack and push itself apart, and the rebar in there resists that load. So there actually is a normal force due to an applied torsion, but forget I ever said that. Doesn't apply to this. Okay, so any other questions about this? That was a very good point, though. That was an excellent question, that the actually loaded members that we talked about before cause normal stress and normal strain. Normal stress is 90 degrees out of plane with shearing stress. So the shearing stress can happen or not happen totally independent of the normal stress. Okay, any other questions for tonight? All right, if not, then I'm gonna wrap it up. We'll finish up a little early tonight. And as always, you can look on YouTube for a copy of this. And we shall see you. Everybody's got homework number 7, so they can work on that over the weekend. Okay, thank you very much. Everybody have a great weekend.